Hello everyone and welcome to section 5.1, which is really the second section in chapter 5. It's called Estimating with Finite Sums, or the way that we normally remember this section, I call it RAM. RAM stands for Rectangular Approximation Method. There are a lot of calculations to go with this section, a lot of calculations. I went ahead and did them ahead of time on my scrap paper, so when I write numbers up, I'm not doing them in my head, and I don't expect for you to do them in your head. Okay? Let's try out a new word. We talked about this a little bit last time. Today we start talking about the other half of calculus, which is the integral. There's differential calculus, which is derivatives, and there's integral calculus, which is integrals. Integral calculus was discovered by Sir Isaac Newton at the same time that Leibniz was discovering differential calculus over in Germany. Surprisingly, these two were not friends, and Leibniz claimed that he invented it first, but he changed the dates on his paper, so we don't know, and Newton was bizarre. Anyways, let's get into this. The concept of an integral. Before we talk about an integral, let's talk about a derivative. Remember, a derivative is a slope or it's a rate of change. So it's either the slope of the graph or it's how fast something is changing over time or over something. An integral is the opposite of that. The rest of the year is all about integrals, so we're going to start with the basics. An integral is the opposite of a derivative, or the antiderivative. Integrals and derivatives cancel each other out. It is the net change over an interval. So an integral has an interval. How much have you changed over this time? And we will spend a lot of time talking about that. That's a huge conceptual concept. Huge, huge calculus concept. Graphically, it's the area under a curve. And this is what we're going to focus on today. The area under a curve. We're going to talk about how to calculate an integral, estimate it, based on the area under a curve. Opposite of derivative. What's the derivative of position? Well, the derivative of position is velocity. Then what's the integral of velocity? If I work backwards, what's the integral of velocity? I'm back to position. If you remember a long time ago, I gave you this chart. Position, velocity, acceleration. If you go this way, you're taking derivatives. If you go this way, you're integrating. So derivatives go down through those three, integrals come back up. Much more about this to come. Much, 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 much more. But that's the basic idea, that an integral is the opposite of a derivative, or the inverse of a derivative. What if velocity is not constant, and you have this graph? So this is a velocity graph, the blue thing. Let's say I wanted to estimate the area under it. I'm going to draw 4 rectangles that are going to touch on the left side. So 1 rectangle that touches on the left side, 2 left rectangles, 3 rectangles, and 4 rectangles. Those 4 rectangles approximate this entire area underneath the curve. Now, is this approximation, are those 4 rectangles, if I add them together, going to be less or more than the correct area? They're going to be a little bit less because I'm missing those little corners right there. So, how would I do this? Well, first of all, this is called left-hand rectangular approximation method, or I'll call it LRAM from now on. Why is it LRAM? Well, I'm using rectangles to approximate, so that's the RAM part, and on the left sides are touching, so it's LRAM. These are rectangles, and the area of a rectangle is its base times its height. How do we find the base? Well, this one's really easy. We look between the x values. How wide is this base? It's 1. How wide is this base? It's 1. How wide is this base? It's 1. How wide is that one? It's 1. Are they all the same? Yeah, but they don't have to be, and I'll show you that later. How do we find the heights? Are they all the same? Well, the heights are my y values. And I'm only using the left side. I don't use this side because that's the right side of a rectangle. Well, somebody's going to say, but isn't that the right side of this rectangle? It is, but it's also the left side of this rectangle. How do I find those four heights, those four y values? Well, I take this number, this number, this number, and this number, and I'll plug them in to the equation. So how do we find the heights? We plug in the left x value into the equation. Are these all going to be the same? No, because you're getting taller as you go across. Okay? So let's try this problem. Let's do an LRAM problem. My advice, guys, is to make a table. Okay? So, here's my table. My x values are 0, 1, 2, 3, and 4. Those are the x values that I see on this graph. Now, how do I find the y values? I take these numbers and I plug them into the equation. If you plug in 0, you're going to get 1. If you plug in 1, you're going to get 1/8 plus 1, which is 9/8. If you plug in 2, that's 4. 4 over 8 is 1/2. 1/2 plus 1 is 3/2. If you plug in 3, you're going to get 17/8. And if you plug in 4, you're going to get 3. And again, I did those ahead of time on my calculator. So those are the heights. But I only want to use LRAM. In this first rectangle, how big is the base? From 0 to 1, it's 1. In this first rectangle, which of these two heights am I going to use? I'm going to use this one because it's the left side. So my first rectangle is 1 by 1. Plus, here's my second rectangle. How wide is that base? It's still 1. Which of these two heights am I going to use? This one, because it's the left side. 9/8. Plus, third rectangle. How wide is its base? It's 1. Which of these two heights am I going to use? I'm going to use this one because it's the left side. 3/2. The fourth rectangle, how wide is its base? It's 1. Which of these two heights am I going to use? This one, because it's the left side. Now that's all 4 rectangles. If I want the total area, I'm going to add them up. And you get 23/4, which is also 5.75. And we said earlier that's an underestimation. We don't really know the answer right now, but it's an underestimation because you can see I'm not getting these pieces. So that's LRAM, using the left side of the rectangle. Guess what comes next? RRAM, using the right side of the rectangle. Now look at these. These rectangles use the right corners. The right sides touch. Are these 4 rectangles going to over or underestimate the area under the blue line? In this case, it's an overestimation. You can see that the green rectangles are above the blue line, blue curve. So, anytime I do a RAM problem, I'm going to start off with a table. 0, 1, 2, 3, and 4. Okay? And I'm going to get the same numbers when I plug them in. I'm still going to get 1. Still going to get 9/8. Still going to get 3/2. Still going to get 17/8. And I'm still going to get 3. And I'm still going to use rectangles. For this rectangle, how big is the base? Well, the base is still going to be 1. RAM doesn't change the base. But which of these two heights am I going to use? Well, since I'm doing RRAM, the right side, I'm going to use the right one. And the process is pretty much the same. This is still 1, and the right side is 3/2. This is still a base of 1, and the right side of 17/8. And this is still a base of 1, but a right side, this time, of 3. If you add all those up using your calculator, you get 31/4, which is 7.75. And we said earlier, that's an overestimation. That's too much. So we did LRAM and got 5.75, which is too much. And then we did RRAM and we got 5.75 was too little. 7.75 is too much. Is there a different RAM that I could use to be more accurate? Yeah, there is. MRAM. Put the rectangle right in the middle of the curve. MRAM is the hardest one to do, and it's the least used because you're only estimating, so why do I need to be really accurate for an estimation? But I'm going to show you how to do it. Let's make a table. But this time, I don't want to use 0, 1, 2, 3, and 4. What's the middle between 0 and 1? 0.5. What's the middle between 1 and 2? 1.5. Between 2 and 3? 2.5. And between 3 and 4? 3.5. Now how do I get the y values to go along with these x values? I take these numbers and I plug them in up here. And I did this earlier, so I'm just going to tell you it's 33 over 32. It's 41 over 32. It's 57 over 32. And it's 81 over 32. And I'm going to use all 4 of my rectangles. 1, 2, 3. I'm sorry. I'm not going to use the rectangles. I'm just going to look at the bases and the heights. I don't need to draw the rectangles here because I'm not using the left side or the right side. I'm using the whole thing. So for the first rectangle, how wide is the base? It's 1. And the height in the middle is 33 over 32. The next one is still 1, but it's 41 over 32 in the middle. The next one is still a base of 1, but it's 57 over 32. The last one is still a base of 1, but it's 81 over 32. If you work all of that out, you get 58 thirds, which is 6.625. That's probably a better estimation. I don't know whether it's an underestimation or an overestimation because you can see that's over but that's under, so I'm not sure. Okay? MRAM, we don't use it very often, but it's the most accurate. The reason we don't use it is because it takes a lot more mathematics, a lot more arithmetic. So why do we want to use more arithmetic to guess? These examples are 4 subintervals, 4 rectangles. As the number of subintervals increases, so does the accuracy of your RAM. Want to be more accurate? Use more rectangles. The problem with using more rectangles is you have more arithmetic because your table gets bigger. It will tell you how many rectangles to use in the problems. We'll be learning how to find the exact area if we have an equation. RAM is still useful for finding the area under the curve if we do not have the equation. This is big on the AP test, and I'll show you an example of one next. Every year there's always at least one and sometimes more short answer questions that deal with RAM. You have to know RAM. Have to. It's a simple concept, but you got to know what it means. Let's take a look at this. The following table gives us velocity of a car in miles per hour during a road trip. Let's use this table to calculate LRAM and RRAM. So let's do LRAM first. How many subintervals do you think I'm going to use? 1, 2, 3, 4, 5 in this case. Notice something else. The x values, the bases, aren't evenly spaced. So we have to pay attention to that. For this first rectangle right here, how wide is the base? It's 1. Which of these two heights do I use? 0. Plus, for this next rectangle, how wide is the base? It's 2. And which of these two heights do I use? This one. For the next rectangle, how wide is the base? It's 3. And which of the two heights? 81. For the next rectangle, the base is 2, which height? 67. And for the last rectangle, the base is 1, and which height? 70. In this case, I'm going to get, and no, I can't do this in my head, I wrote it down earlier, 593. Now let's do the same problem, but let's not use LRAM, let's use RRAM. Will the bases change? No. The width of the bases, the x values, are going to stay the same. But what does change is the heights. So this first base is 1, but I'm going to use 73. The next base is 2, but I'm going to use 81. The next base is 3, and I'm going to use 67. The next base is 2, and I'm going to use a height of 70. The last base is 1, and I'm going to use a height of 34. If you calculate all that out, you get 610. So the actual answer is somewhere probably between 593 and 610. They're pretty close. Why can't I calculate MRAM? Well, this comes up every time. Why can't I calculate MRAM? MRAM means the middle between these two. Can I figure out the middle between these two? Well, I know the middle between 0 and 1 is 0.5. That's easy. But I don't know what's going on between those two. Maybe it's a line. Maybe it's a curve. But we don't know what is going on between 0 and 73. Maybe it is exactly in the middle. Maybe it is exactly 36.5. But maybe it's way above or way below. I don't know what's happening between 0 and 1. And there's no way to know that answer. Because that, since we don't know, the middle velocities, we can't just guess. When I give you a table, you can't just guess at what's in the middle. If there's nothing there, you can't do the problem. So we can't use MRAM with this. Okay, the last question. What do these calculations tell us? Well, we did RAM. RAM is a way to estimate an integral. Okay? So these are estimates of an integral. If I integrate velocity, in other words, if I integrate velocity, what do I get? What's the antiderivative of velocity? It's position. So remember, this is net change. I told you earlier this is net change of the position now. We normally would call that displacement in physics. Take a note. It's not how far you've traveled. It's how far you ended up from where you started. And we'll spend a lot of time talking about that concept next time. Okay? But that does it for RAM. If you guys have any questions, come talk to me. Otherwise, thanks.